And in fact, this conjecture happens to be true, yielding this kind of differential equation a very special name. So suppose we are given a linear ODE, nth derivative plus a1 of z minus first derivative, and so on until an of z g of z equals to 0, so also homogeneous. Then a specific point, z0, a complex number, is called a regular singular point. Of the equation star if the order of gi at z0 is bigger than or equal to minus I. In other words, if gi has a pole of order less than or equal to I at z0. This of course doesn't mean that ai has to have a pole at z0 at all. So now, what is the intuition? That these kinds of equations give us multivalued functions. And the reasoning for this lies in, let's say, some statement that you use generally when proving the Picard Lindelöf theorem. So the theorem that tells us that like ODEs always have solutions. And this is like corollary on the way to proving Picard Lindelöf. Let this differential equation star have only regular points on some domain U. Then for every point z0 in U, there's a neighborhood V that contains that point, and an n-dimensional vector space. Let's call it O with a subscript star, so the differential equation of V of holomorphic functions F on that neighborhood to C that solve star. So what this tells us is that, well, we can always solve this equation locally, and in particular sort of around every point on our set of regular points. And the way you then sort of go on to prove Picard Lindelöf, i.e. the existence of sort of solutions with a maximal domain, at least on the real line, is that you say, well, neighborhoods are really boring. In particular, you can sort of replace the word neighborhood by open ball. So then around every point you have an open ball where the solution can be defined. So then you can just start at your point, go near the boundary, and then say, well, around that point we now also have a local solution. Maybe it's bigger, maybe it's not. So let's say it's that interval. Then you go again near the boundary, you do the same thing, and then using some sort of Zorn's lemma maximality thing, you really get that like you have a unique, well, given some initial conditions, have a unique maximal domain and a unique solution. The problem is, if we're doing this with complex numbers, is that you start out with a point and then you get like an open ball around it. Yeah, let's say our singularity is this point. Then you go near the boundary and there's another open set with solutions, or with like unique solutions. Then you go near the boundary, get another set of unique solutions, blah 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 blah, and you can maybe guess where this is going. And then sort of after going once around in a circle, you end up with a different solution. So you might start here with some set of initial conditions, say, okay, I can extend this function to this domain, starting from the value it has at this point. I can extend it to this domain, then starting at this point, you can extend it to another domain, and once you've sort of gone around your singularity, you see that you have some sort of contradiction. And this is exactly what we had with the logarithm and some non-natural power before. So the problem is, in complex numbers in 2 dimensions, you can go around things. And this is fundamentally the problem that arises when you view this in complex numbers instead of only real numbers. And one other thing to note is that since we started off with a homogeneous linear ODE, of course our solutions form a vector space, and to sort of not have to deal with the question of initial conditions, I'm just saying that this vector space has dimension n, which happens to be the order of our differential equation.